Okay, so for today, guys, okay, with the physics unit, same as we did before, we'll go over kind of the key stuff. I'll tell you kind of what things are going to be big marks on the final exam from the physics unit, okay, so that you can kind of streamline your studying there. Okay, so first thing we covered, okay, types of energy. And those would definitely be in the multiple choice sections. That would be like chemical energy, okay, kinetic energy, electrical, magnetic, okay, those kinds of things. So just be able to identify it in a certain situation. Okay, so like I said, just general recognition. Okay, I think on your unit exam was like, what is the energy possessed by a tank of propane or something like that, or a rolling ball or something like that. Okay, just be able to identify, okay, what would be the main source of energy there. Okay, and then we talked about thermodynamics. Okay, you'll definitely need to know the laws of thermodynamics. Okay, first law, second law. So first law of thermodynamics is the law of conservation of energy. Okay. Second law of thermodynamics, we actually talked about a fair amount in the last unit as well. Okay, so energy transfer from hot to cold, high to low. And I would say you probably also need to know about the types of systems, because those go along with the laws of thermodynamics: open systems, closed systems, isolated systems. Okay, and that's, again, going to be likely to be multiple choice, although the second law of thermodynamics does come into play probably in a few written response items for the last unit. Okay, we're talking about winds and convection and conduction. That's all second law of thermodynamics stuff, so it kind of ties in there. Okay, but the questions about just the laws of thermodynamics themselves would likely be multiple choice items. Okay. All right, we also talked about heat engines and heat pumps. Okay, in that same lesson, could be some multiple choice items about those. There are, after all, quite a few multiple choice questions. Okay, then from there we went on to scalar and vector quantities. Okay, do you need to know which quantities are scalar and vector?
Yes.
Okay, will I try to burn you again the same way I did on the unit exam?
Yeah.
Yeah. Remember how I did that?
Down.
Yeah, with that acceleration question. Okay, I asked, what would the final velocity of this object that was like dropped or was rolling down a hill? It was down the hill, I think. Okay, it was rolling down a hill. What would the final velocity be? And you guys, like, a whole bunch of you did the question just perfectly fine and then wrote just a number. I believe it was 8.14 meters per second, and then didn't put downhill after, okay, because it was asking for final velocity, which is a vector quantity. So you definitely need to know it in that context so as not to lose another mark for the same thing if you were one of the people who lost a mark on that. You weren't alone, because most people forgot that, okay, on the unit exam. So we got to know which ones are scalar, which ones are vector for that reason. But we also need to know because sometimes you treat them differently when you're doing your calculations. Okay, so we need to make sure that we understand which ones need to have a vector and which ones don't. Okay, so on that note, okay, V equals D over T, V equals D over T. Okay, vector quantities, that's written response. WR is written response, so that's the thing I just told you about. Okay, and you could get some sort of problem where you're solving for a vector quantity and you need to treat it as such. Okay, now you're not likely to get a V equals D over T problem in the written response because, well, that's kind of beneath you at this point, but it could be a multiple choice question. okay? Because that's a pretty simple manipulation and calculation. So expect you'll see that on the exam, but more than likely in the multiple choice. Okay, other thing to remember, how do we calculate displacement? Okay, it's final position minus initial position. That might even come up on a graphing question. If you were to get a position versus time graph, that could be important.
We get all the formulas here.
All the formulas. You get exactly the same thing that is on your periodic table. You're just getting a fresh one for the final. Just obviously some of you have lost yours, or it's really beat up, or you've written a complete encyclopedia all over it. Okay, so you get a fresh one. Okay, then acceleration. All right, so we need to be able to do a written response problem, okay, on acceleration, very much like the two that were on your unit exam. Okay, and then graphing. Graphing's huge. Okay, you'll definitely get graphing on your final exam in both parts of the test. Okay, the skills you're going to be expected to demonstrate, okay, same things you did in this class. Interpret a graph. Tell me what's going on in a graph. Make simple calculations from a graph. Like if you got a position time graph, that you'd be able to calculate the total displacement or the total distance traveled or the average velocity. Okay, if you had a straight line on that graph, that you might be able to use y equals mx plus b. Okay, same with your velocity versus time graphs. Okay, expect both will be on there as we did after. I'll do a lab on each one. Okay, so read and interpret, okay, extrapolate, y equals mx plus b, okay. Now, something that a few people missed on the unit exam, okay. A few people on the unit exam looked at the graph and went, oh, it's a graph, I'll just use like v equals d over t or something like that, even though they were given the equation for the line, okay. If you were given the equation for the line, should you use the equation whenever possible? Mm-hmm. Yes, especially if the question says, using your graph, and I think on your exam it even said, and the equation for it, okay? If it says that, it's telling you, I want it done this way because I've set it up so you get it wrong if you don't. Okay, that's what that means in code. All right, so using your graph, use the graph. And if you have the equation, use the equation whenever possible. Okay. Okay, position versus time graph. What can I get off a position versus time graph? Okay, I can calculate velocity. What else?
Displacement.
Displacement. What else? Kind of like displacement except scalar. Distance. Kind of like velocity but scalar. Right. Can I also get position and time?
Yeah.
Yes. Okay, those are the things I can read directly off of that. Can I infer what type of motion is going on? Okay, if it's a horizontal line, what's the object doing? Yeah, it would be the same speed, but that's right. It would be 0 meters per second. Okay, so I mean, yeah, that's sort of right. Except the speed would also be 0 meters per second. The object would not be moving. Okay, what if it's angled upwards?
Constant speed.
Constant speed, because it's changing its position at the same rate every time. Okay, and if it's curved, Jeff, then it's accelerating. Okay, because then it's changing its position at a non-uniform rate. Then the only way that happens is if it is going faster. Okay, so you could definitely get questions where you'd be asked to do that kind of interpretation. Okay, so I could give you, okay, any of these types of things here. Okay, if I give you a graph that looks like the one here on the left, okay, and it's kind of all over the place. Obviously, you won't be given the equation for that graph because there isn't one. Okay, so in that case, if I asked you for what's the average velocity, well, then you would use final position minus initial position and divide it by time. Okay, everyone follow me there? If I asked you for the average speed, then you would go, okay, how far did it go in this part? 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 And divide it by time. Okay, different ways to calculate that. Is that ringing a bell? Okay, if you're given just a simple linear function, okay, then y equals mx plus b, and the velocity of the object is equal to the slope. Okay, because the slope of this line tells you the rate at which the position changes as a function of time, meters per second. Okay. All right, so little things like that to remember. Okay, this is kind of where we get that from. Y minus b over x is final position minus initial position over time. Okay, that's where that all comes from. Okay, if I was to give you, okay, sorry, we could calculate all of these things. Okay, we've already talked about that. Displacement, final position minus initial position, distance, add all the sections together. Okay, now if I give you a velocity versus time graph, what can you read off of that? Velocity and time. Okay, and what can I calculate off of that? Displacement and acceleration. All right. We were asked to do both of those things in our analysis in our Need for Speed lab. Okay, so we got to be able to do that again. Okay, so if I'm looking at this graph here, okay, if this question has, or this graph is on a question, the question asks for the average acceleration, that would be the final velocity minus the initial velocity divided by time. I wouldn't be able to use the slope because I don't have one. Okay? There's no equation for the line on that graph. But if I was given a linear function like this, then I would do y equals mx plus b, and m would represent my acceleration because it would be in meters per second squared, meters per second per second. Okay, and that's where we get this from. M equals y minus b over x. On this graph, that's vf minus vi over t. Okay, what if I'm asked to calculate displacement?
The area underneath the line.
Right, the area underneath the line. Here's why. Okay, if I calculate the area underneath the line for this graph, actually for this graph, I could simplify it and it would just look like this. Okay, what I'm doing is taking the average velocity and multiplying by time. Anywhere where the thing is a rectangle, the average velocity is just whatever the velocity is because it's not changing, multiplied by time. So that's base, time, multiplied by height, velocity. Okay, if it's a triangle, then I go base, the time, times the height, divided by 2, because the height over 2 is the average velocity, because the velocity is changing. During that part, the object is accelerating. Okay, so that's why we do that for those. Okay, it was another thing you were asked to calculate, okay, on your lab, so expect it's probably going to be something you'll be asked to calculate on your final. Okay, so now I've got all that written down here. Okay, so if I had a graph that looked like that, okay, what I'm really doing is average velocity times time. Okay, and so I would calculate the area of all the shapes, okay, and put them together. Okay, is that ringing a bell? All right. After graphing and acceleration, then we moved on to work energy theorem. Okay. Now, in work energy theorem, if work is done, what's going to change? Energy, because work is a change in energy. Okay? So, if I do work, then I'm going to change the mechanical energy of the object. In Science 10, that means either the potential energy or the kinetic, but never both. Physics 20, we do them with both. Okay? So, there's going to be either a change in kinetic or a change in potential. How do I tell which one's changing? If kinetic energy is changing, what is changing for the object? It's velocity or speed, okay? Because it's got to be accelerating, okay? Kinetic energy has to do with how fast you are going, okay? Whereas if you're dealing with potential energy, what's going to change about the object?
Height.
It's height or position above the ground. Okay, is that making sense to everybody? Those are the things we look for. Okay, so to solve a work energy theorem question, okay, there could be some understanding stuff in the multiple choice, like being able to identify situations where work is being done. Okay, and then obviously problem solving in the written response. Okay, work is force times distance and a change in energy. Okay, so that means that it's final energy minus initial energy. Okay, and that could be m times g times h, or 1/2 mv squared. Okay, most of the time when we did these problems, what we ended up with was force times distance equaled like 1/2 mvf squared minus 1/2 mvi squared, or force times distance equaled m times g times h final minus m times g times h initial. Okay, and most of the time the initial was what? 0, usually. Okay. Okay, is that ringing a bell? Okay, definitely expect one of those, 1, okay, on your final. Yeah, 2 on your unit exam. Okay, and then we did conservation of mechanical energy. That's that whole EI equals EF. Okay, those are the roller coaster, or the kid going down the hill in the sled, or any of those kinds of questions. Okay, in those questions, there is no work being done. Energy is being conserved. Okay, so that's EI equals EF, okay, and then we said, right, mechanical energy is the sum of an object's potential plus kinetic, so this is initial mechanical plus or equals final mechanical, okay, and then you could get a question like this. Okay, where I ask you what's the final height of this object. Okay, if it's initially 20 meters above the ground, moving at 4 meters per second, a little while later it's moving at 10 meters per second, find the final height. Why don't you guys try that one right now? See what you remember. Give me a couple minutes on that one. Okay, so first thing we have to recognize is that this is an isolated system, so energy is conserved. No energy is being lost to sound or anything like that. Okay, so the 20 kilogram mass starts out with some kinetic energy. It's moving at 4 meters per second. It also has potential energy. It's 20 meters above the bottom of the hill. Okay, a little while later, it's probably not at the bottom of the hill, okay, because they're asking us what the height is, and it's moving faster at 10 meters per second, so it still has kinetic energy. Okay, so if we're going to calculate what its height is, okay, then we have to set this up. We have to say that the initial mechanical equals the final mechanical. That's step 1. Okay, expand that out to the initial potential, which we know we have, plus the initial kinetic, which we know we have, is the final potential, which is what we're looking, well, part of it is what we're looking for, plus the final kinetic, okay, which again we know we have. All right, so if I'm looking for something that's part of final potential, what should I do with final kinetic? Subtract it over to the other side. Okay, that isolates my final potential, so that's what I've done here. Okay, EKF is now on the other side. Now I would expand those out so that they're in their full formula form. Okay, that would be mghi plus 1/2 mvi squared minus 1/2 mvf squared equals mghf. I can cancel off the masses because mass is in every term. I don't have to. okay? I can leave the mass in there and put 20 in 4 different times, okay? But that's up to you. And then if I want to get HF by itself, all I do is divide both sides by G, okay? And I'll have HF by itself. Then I plug in my numbers, okay? So 9.81 times 20 meters, times 20 meters plus 1/2 times 4 squared, that was my initial speed, okay? Minus 1/2 times 10 squared equals my final height, which is 15.7 meters. Okay, so if you got that one right, good on you. You know how to do that still, which is good, because that test was like before Christmas. Okay. Okay, and then the last thing in that unit was efficiency. Okay, the only efficiency question will be like the efficiency question you had in your unit exam. It's a multiple choice question, simple calculation, and what is efficiency? Make sure you understand that.
I got a question about solar panels.
Okay.
What do you do when they get covered in snow and on your roof?
You either accept that they're going to do nothing for you during that time, or you have a brush or like a roof shovel that you can use to clean them off.
So that you can produce.
So that you can
what
produce.
you do in the summer.
Yeah, because it's cloudy, or because the sun is low angle and you're only getting 6 hours out of the day, but yeah. But I've noticed like the people in my neighborhood do not clear theirs off, and some of them can reach them, but they don't clear them off. If it were me, I'd have an extendable roof shovel, and I'd be clearing them off. Like, I'm gonna pay for those things, they're on my roof, I would be using them.
Is there heated solar panels?
You can get apparently ones that you use heat to melt the ice off them, but then the return on what you get from them after you've used heat to melt them is diminished, right? Yeah, because turning electricity into heat is like the least efficient thing you can do. Most of them melt pretty quickly because the panels themselves are fairly dark. But if they're covered in snow, and your roof, depends on your roof slope too, right? If your roof pitch is a little steeper, then they're more directly facing the sun, they're gonna melt more quickly. What's that? It depends on how it falls on them initially, right? Like this last batch of snow, there's some panels in my neighborhood that are still covered. Okay, and it's been a while since we had the snow. So if you get that light fluffy stuff, stays cold for a while, like if it gets warm, sun comes out, they'll clear off, especially if you have a steep roof pitch. Okay, that's one of the things they really liked when we got our house estimated for it, was that not only did most of our roof pitch face south and west, but it was steep. Okay, so we were going to get direct sunlight a lot, and they would clear quickly. So I don't know. Some of them you can also get like a motorized thing that'll like lift them so that they're vertical and stuff falls off. That'd be the way I would go rather than have a heater. But yeah, like the ones that are out in Aldersyde, nobody cleans those off. Like every time I drive by them after it's snowed, they're covered in snow. We had this discussion, didn't we? Where I said you should pay the guy minimum wage to go out there with a big broom and brush those off. Like, what's that? You're just trying to distract me? Well, it's your review. You can distract me all you want. I'm done teaching the course. I did my job already. Okay, so yeah, just make sure you know how to use that efficiency formula. It is on the back of your formula sheets, like V equals D over T, so it's not terribly hard to use. Okay, so on your final, oh, no panic. A panic attack here. I was in the wrong folder. Thought I'd lost it. Yep. Okay, so on your final exam, guys, there are, for physics, okay, whoop. 1, I think about 12 multiple choice questions. Okay, on physics. Ranging on stuff from efficiency, V equals D over T, scalars, vectors, graphing, energy, graphing, thermodynamics, energy, yeah. Okay, and then for the written response, there are 4 questions on physics in the written response. All problem solving on the things we discussed. Okay, now, yeah, I don't know if you guys want to write this down, I'll give this information to you. Okay, so for chemistry, there are 16 multiple choice. And there was one with a person's name in it. For chemistry. One question with a person's name in it. You can imagine that it might be one of 2 very, very important people. Okay. And then there's stuff on atomic theory, stuff on properties of compounds, solubility, naming compounds, polar nature of water, chemical and physical changes, naming, reactions. So. And there are, looks like, about 11 questions on biology in the multiple choice. What's that? Okay, and they're on the, well, we said that the cell diagram was going to be in the multiple choice, so there's 1, 2, 3, 4, 5 questions on that, so 5 of the 11. And then there's some plant transport, plant growth and development, multicellularity. Okay, we already talked about the physics ones, and then there are 10 questions on, 11 questions on global systems. I think that adds up to 50. And they're on like soils, biomes, water cycle, energy transfers, latent heat, heat capacity, energy transfers, heat capacity. Okay, then in the written response, like we said, there are, so there's a question on balancing to start off, 3 reactions that need balancing. Then there's a question, there's just a reaction question, where you just have to take it from words and write it out in formula form, identify the type and balance. And then there's a predict a reaction question.
So, 3 for chemistry?
For chemistry, and then there's 2 mole equation calculations in question 4. And then there are 1, 2, 3, 4 written response for biology. And they are plant transport, cell transport, plant growth and development, cell transport. then we talked about physics. You got work energy theorem, graphing, acceleration, conservation of energy. And then there are 3 questions from global systems. One is about energy transfers, heat transfer. I put another biome with a climate graph in there, and a latent heat problem. Okay, so that gives you a pretty good idea of what you need to look at to help streamline your studying. Okay, there's a work energy theorem problem for you. Why don't you give that one a try? Okay, how do I know, besides the fact it says work energy example number 1, that this is a work energy theorem problem? Am I ever asked or given force in a conservation of energy problem? No. Okay, the other thing I know is that only one type of energy is changing in this question, and it's what? Potential. Okay, in a conservation of energy question, 2 types have to change. All right, so right off the bat, I know that in this question, the work that's being done is going to change the potential energy of the ball. Okay, now, I'm supposed to find the force, so obviously that's got to be there. Okay, so force times distance is going to equal my final potential energy, m times g times h final, minus my initial potential energy, m times g times h initial. Now, since it's asking me to find that or telling me that the height is 21 meters, where most likely did I throw it from? So what's my initial potential energy? 0. Okay, so now I've got this set up. Now I should be able to solve for my force because I have all the other things. They told me the mass, 1.5 kilograms. They told me the final height, okay, 21 meters. They told me the distance, 1.5 meters. They told me the initial height, sort of, okay, 0 meters. So I have all of that. So all I need to do is divide both sides by d. Okay, and so what that's going to mean is, okay, simply going F equals 1.5 times 9.81 times 21 meters divided by 1.5 meters. Okay, since I don't have my calculator started, I'll hope that I have the answer down there. I do. Okay, 206 newtons. Okay, for the force required on that one. Okay, everybody all right with that? Okay, let's have you try that one. So in this one, what kind of energy is changing? Kinetic. It's asking about speed, right? Okay, so if that's the case, I'm just going to erase all of this stuff here. Okay, so our givens are, well, first off, that the work that's being done is changing the kinetic energy. Okay, our givens are the mass, 1,000 kilograms. Okay, the force, 500 newtons, which isn't very much. Okay. The initial speed and the distance. So this is more like a car being pushed, okay, by like 2 people. Okay. So work is the change in kinetic energy. I'm going to expand that out to force times distance equals 1/2 mvf squared, so my final kinetic, minus 1/2 mvi squared, which is 0 because vi is 0. Okay, so now I just need to find its final speed. Okay, so I'm going to divide both sides by 1/2 of m. Cancel from over there, and then I'm going to square root to get vf. Okay, so when I plug in my numbers here, right, what I'm going to have is 500 newtons times 15 meters divided by 1/2 times 1,000. 1,000, not 100. 1,000, there we go. Okay, so square root of, in brackets, 500 times 15 divided by 500. Okay, so final speed will be 3.9 meters per second. Okay, questions on that one? Okay. Well, what else have we got here? Okay, so let's say I give you this position versus time graph, okay, and I give you that equation there to go along with it. Okay, calculate for me the following things. Position at 25 seconds and time to a position of 67 meters. Okay. Okay, what axis is position on? Which axis is position on? Y-axis. Position's on the y-axis. So in this one here, I'm being asked to solve for y when x is 25. Okay, so if I'm plugging in those numbers, okay, we're going to have 4.5 times 25 plus 6. Okay, so it'll be 118.5 okay, meters. Okay, for part A. Everyone all right with that? Okay, for part B, I'm looking for the time. Time is on which axis? X. So now I've got to manipulate y equals m times x plus b for x. So I'm going to subtract b from both sides, then divide both sides by m. That'll get me x. Okay, so I'll have 67, the y value they gave me, minus 6, which is b, and then divide that by 4.5, which was the slope. All right, so that should take 13.6 seconds. Okay. Questions on either of those? Okay, is that graphing stuff ringing a bell?
Yeah.
Okay. Okay, let's see what we remember about solubility. Okay, so let's say, because this is probably the way I would do it on the test, let's say that I give you this reaction, and I ask you, which, if any, of the products are soluble? Okay, what do I have to do first? I have to do a double replacement reaction and predict the products. I can't figure out which of the products are soluble if I don't know what the products are. Okay, so since it's a double replacement reaction, I switch the metals. So that means that PB will end up with I, and sodium will end up with nitrate. All right, both of those are ionic compounds. What do I have to do with them? Okay, this one's okay right here. This is a -1, this is a +1, so that one works out. But for this one, lead can be a 2 or a 4. It's a 2. Okay, if I look over on this side, knowing nitrate's a -1 and there's 2 nitrates to make up for this one, okay, it must be a 2. Okay, iodine is a -1, so I'm looking at PbI2 here. All right, so now I need to look at my solubility chart. Okay, so, okay, on my solubility chart, okay, I see that nitrates are basically all soluble. Okay, it says nitrate here, soluble with most, except for these incredibly rare things that are not in this reaction. Okay, so sodium nitrate definitely soluble. Okay, now I just have to see if lead nitrate or lead iodide is soluble. So I look at iodine here. It says it's soluble with most things, but not with copper 1, silver, mercury 2+, lead 2+. Okay, so this one, not soluble. That one was soluble. So if this was a multiple choice question, I'd be looking for which one of the options said, PbI2. Okay, because you'd probably get neither sodium nitrate, lead 2 iodide, or both. Okay, those would be your options on a question like that. Okay, that sort of makes sense? Okay, so that would be a pretty standard kind of solubility precipitates question. How did we just jump to chemistry?
That's what I was wondering.
Magic.
I didn't even notice that I did that.
Magic.
This must have been a question somebody asked when I was making this one up. B4. Okay. See if we go back. Oh, okay, here we go. Here's a good one. Okay, that's a physics question. That's a physics question. Okay. Nail falls off a building. How fast is it going after 3.5 seconds? And I'll give you that acceleration is 9.81 there, even though in a question like that on a test, I totally wouldn't give you that. I'd expect you to know that that's the rate at all things fall. You can. Okay, so like I said, if you got this one on a test, I would not give you the acceleration. And I'd expect that you know things fall at 9.81 meters per second squared. The other trick to this is, what's VI? 0. Okay, you didn't throw them off, they fell off. Okay, if it's asking for how fast, speed or velocity? Speed, so I don't have to put a direction on that. Okay, and we know that it's falling for 3.5 seconds. Okay, so A equals VF minus VI over T, and we're manipulating for VF, so multiply both sides by T. VI is 0 anyway, so we can just get rid of it. T times A will get us VF, 3.5 times 9.81. Okay, and I think the one on your test is actually basically the same as this one. Okay, so 3.5 times 9.81. Okay, so 34.3. Actually, we only have 2 significant digits, so it would just be 34. Okay, everybody all right with that? Yeah? Okay. I'm sure we got something else here. Oh, why do I have biology stuff in there? We don't need that. Okay. Anything else you guys would like to go over a request for physics? Yeah, any questions from you guys? I mean, tomorrow's your Q&A day. You got to come with lots tomorrow. But
We should do an efficiency question.
an efficiency question. Okay.
Really?
Okay, so remember I said there's two efficiency multiple choice questions? One of them works like this one. Okay, it's a simple and efficiency calculation. I can't remember if you had to find the input energy or if you had to find the efficiency or the useful work, I don't remember, but it's something like this. All right, so we're looking for the input energy, okay, so that's EI, okay, and we're given the useful work, 1600 joules, okay, and we're told the efficiency, okay, which is 31% or 0.31, okay, so efficiency is the useful work divided by the input energy. So if I'm looking for the input energy, I'm just going to switch efficiency and input energy. So if input energy is going to be the useful work divided by the efficiency as a decimal, okay? So that's going to be 1600 divided by 0.31. Yeah, I have to do it that way because the input energy has got to be significantly more than the useful work that was done if we're only going at 31% efficiency. So 1600 divided by 0.31 tells us we would have needed 5,161 joules. Or actually, we would say 5.2 times 10 to the 3 joules. But I will not be asking about significant digits at all on your final exam. Plus, that would probably be a multiple choice question, as I said, where you just have to find the number that you got in the answers. Now, keep in mind, you need to start preparing yourself for how multiple choice questions involving calculations get made from here going forward. We think of all the ways you could possibly do it wrong. We do it that way, and we put that in as one of the answers, just so you know, okay? Because I have seen people come out of like tests, diploma exams especially, like, man, I did so awesome. Every answer I found was on there, and we're like, oh, that doesn't mean you did good. Okay, I'm glad you feel good about it, but that doesn't mean you did good. Okay, it just means the people who made up the test are cruel and unusual, okay, and they figured out all the ways you could do it wrong, did it that way, and put the answers on there to make you feel good until they crush you later. Okay, savage, yes. Okay, so just be aware of that. Oh, totally. Yeah, yeah. Okay, so tomorrow, come with questions, okay? Whatever it is you want me to cover, I'll make up a question about it. We'll go over it. I'll review it. We'll do whatever it is you need tomorrow, okay?